All right, strap in everyone, because today we're diving headfirst into some serious
Oh,
physics.
that's gonna be good.
Yeah, we're talking about a concept that's trying to solve one of the biggest mysteries in science.
Hmm.
How to bring together those two giants, quantum mechanics, the world of the super tiny,
Right.
and general relativity, the realm of the superhuge. And get this, it might just rewrite our understanding of time itself in the process.
I love it already.
It's called the time force hypothesis.
What's so fascinating about this hypothesis is that it doesn't just try to, tweak the theories we already have. It's saying, what if we've been looking at the universe the wrong way this whole time?
So instead of trying to jam those two giant puzzle pieces, quantum mechanics and relativity, together, the time force hypothesis, or TFH for short, is saying maybe we need a whole new puzzle.
You got it. TFH proposes this wild idea that everything, and I mean everything, exists and interacts within this thing called a four-dimensional scalar field. Think of it like an invisible ocean of energy that's everywhere all throughout the universe.
Okay, hold on. Four-dimensional ocean, I'm already lost.
Aha. All right, let me break it down. So, we usually think of the universe in three dimensions, right? Length, width, height.
Yeah, makes sense.
But TFH throws in a fourth dimension, and it's not time like we normally think of it. This fourth dimension is all about energy and how it flows in ways we can't really picture, kind of like waves moving through water, but, in higher dimension.
So where does time fit into all of this? Is this fourth dimension, connected to time somehow?
Exactly. That's where TFH gets really interesting. It says that time isn't actually a fundamental dimension like those first three. Instead, it emerges, it kind of pops up as a consequence of energy flowing through this four-dimensional field.
So let me see if I get this straight. Time isn't this separate thing ticking away in the background. It's actually created by the movement of energy in this field.
You nailed it. Picture this. You're watching a ripple spread across a pond. The ripple itself isn't time, right?
Right.
But the fact that it's moving outward, that gives you a sense of time passing. TFH says that same kind of movement, but of energy through the scalar field, is what creates our experience of time.
Whoa, okay. That is mind-bending stuff. But if that's true, does it mean that our sense of past, present, and future, is it all just an illusion created by this energy flow?
It's a really profound question, and TFH definitely challenges our usual view of time. If time is emergent, just a side effect of this energy dynamic, then it means there's no universal clock ticking away somewhere out there. Time is relative. It depends on your position within this flow of energy.
Wow, that is a lot to process. But the really cool thing is that TFH doesn't just stop at redefining time. It goes on to explain the fundamental forces of the universe in a whole new way too, right? Like, how about gravity, for example? How does TFH explain that?
Well, right now, physicists understand gravity through Einstein's theory of general relativity, which says that gravity is a curvature of space-time caused by massive objects. But TFH takes a totally different approach.
So no more warped space-time.
Yep. TFH asks, what if gravity isn't about space-time bending at all, but about how mass affects the flow of energy in the scalar field?
Okay, now I'm intrigued. How does that work?
Imagine it like this. Objects with mass, things like planets or stars, they absorb some of the energy from the scalar field, and this creates what you could call an energy deficit around them. That deficit then affects how energy flows in the surrounding area, almost like creating a dip or a slope in the scalar field. Other objects then move towards the massive object because they're basically following the flow of energy down that slope.
So it's not that space-time itself is bending, it's more like the energy is flowing differently around massive objects.
Precisely. And the steeper that energy slope, the stronger the gravitational pull. It's a completely different way of looking at gravity, but it creates those same observable effects as Einstein's theory.
Wow. So instead of warped space-time, we have an energy slope. It's like trading in a super complicated machine for something much simpler.
And that's one of the things that makes TFH so appealing to some physicists. It offers this simpler, more unified way to understand the universe.
Okay, so gravity gets a makeover. What about the other fundamental forces? We've got electromagnetism, the strong nuclear force, and the weak nuclear force. Where do those fit in with TFH?
This is where things get even cooler. TFH says that all those forces are just different versions of the same underlying thing, energy interacting within this four-dimensional scalar field.
So like with gravity, it all comes back to that scalar field.
You got it. Think back to that ripple analogy, that ripple moving across a pond.
Okay, yeah.
Now, imagine that ripple vibrating at a specific frequency. That's kind of how TFH explains electromagnetism. It's all about oscillations or vibrations in the scalar field, but at particular frequencies.
So things like light, radio waves, X-rays, all those are just different frequencies of vibrations in this scalar field.
Exactly. It's
Mm,
like the universe is playing this giant symphony, and each force is a different instrument.
I love that. The universe is a symphony. So then what about the strong and weak nuclear forces? What instruments are they playing?
Well, those forces are a bit more subtle. They operate at these incredibly small scales inside atoms. TFH proposes that these forces emerge from what it calls resonance zones in the scalar field.
Resonance zones, what are those?
Okay, picture certain areas in the scalar field where the energy oscillations are super intense and stable, almost like tiny whirlpools of energy. Those resonance zones are where the strong and weak nuclear forces do their thing.
So the strong force, the one that holds the nucleus of an atom together, and the weak force, which governs things like radioactive decay, they're both just expressions of these energy whirlpools.
Exactly. It's pretty different from how we traditionally think about those forces, but it fits perfectly within TFH. It all boils down to the dynamics of that scalar field, just expressed in different ways.
Okay, I'm starting to see how this time force hypothesis, this TFH, is painting a whole new picture of the universe. It's like gravity, electromagnetism, those nuclear forces, they're all just different melodies played on the same instrument, this scalar field.
I like that analogy.
But, I bet there are some folks out there thinking, hold on, isn't this all a bit too out there?
Yeah.
What about all those tried and true theories we already have?
Mm.
The standard model of particle physics, that's been pretty successful.
Right, you're right. There are definitely places where TFH bumps up against our current understanding of physics. Take the Standard Model, for example. It's been amazing at describing how particles behave, but it relies on all these, arbitrary constants and separate fields for every force.
It's like it's got a bunch of knobs and dials that physicists have to constantly tweak to make it all fit together, right?
Exactly. And that's where TFH steps in and says, hey, maybe we can simplify things. Instead of all those separate fields and constants, what if we just have this one fundamental scalar field? Everything else just emerges from how it behaves.
So it's like TFH is giving the whole system a makeover, getting rid of all the clutter.
Yeah, exactly.
But how does it explain the particles themselves then? Like an electron, it has mass, spin, charge. The Standard Model says those are just built-in properties.
Right, but TFH throws a curveball there. It asks, what if those properties aren't actually fundamental to the particles? What if they emerge from the scalar field itself?
So instead of thinking of an electron like a tiny little marble with its properties already set, TFH is saying it's more like a swirling vortex of energy in this scalar field.
Exactly. Imagine this tiny vortex of energy spinning within the field. The amount of energy caught in that vortex, that's its mass. The way it's spinning, that dictates its spin. And any wobbles or asymmetries in the vortex, those give rise to its charge.
So it's not that the electron itself has these properties, it's that the scalar field is behaving in a way that makes those properties appear.
You got it. And the really neat thing about this idea is that it could explain why all electrons or all protons are identical. They're not separate little entities. They're all just different expressions of the same field dynamics.
That is so elegant. It's like the universe is this giant loom, and the scalar field is weaving all these patterns that we see as particles. But what about Einstein's theory of relativity? Does TFH just chuck that out the window?
Not quite. Remember, Einstein showed us that space and time are intertwined. They form this fabric we call space-time. TFH takes that and runs with it. What if space-time itself is just another way the scalar field manifests?
So instead of space-time being this separate thing that can warp and curve, it's actually part of the scalar field.
Right. And this new way of looking at space-time has some cool implications for things like time dilation. Where time slows down near really massive objects or at high speeds.
Oh yeah, time dilation.
Yeah.
That's got to be one of the weirdest things in physics. How does TFH explain that then?
Well, think about it this way. If time is a consequence of energy flowing through the scalar field, and remember, massive objects create those energy deficits we talked about,
Right.
then it makes sense that the flow of energy, and therefore time, would be affected by those massive objects.
So near a supermassive object, the energy flow slows down, and time slows down with it. So the energy is getting thicker, stickier near the object, and that changes how fast things happen.
I like that. A great way to visualize it. And it's not just mass that can do this. High speeds can also mess with the scalar field, leading to those same time dilation effects.
But hold on, doesn't that clash with our everyday experience of time? We all seem to experience time flowing at the same rate, right? Whether we're next to a black hole or just sitting here talking.
You're right. The effects of time dilation are usually really subtle, only noticeable in extreme situations, like you said, near a black hole, or if you're traveling close to the speed of light.
Yeah, right.
But even those subtle effects, they've been measured, there's experimental evidence, and that just reinforces the idea that time isn't this absolute unchanging thing we often take it for granted as.
Okay, so TFH puts a new spin on gravity, rethinks space-time, even offers a different take on time dilation. I'm starting to see why some physicists are so intrigued by this theory. But doesn't it challenge some of the other really fundamental laws of physics too? Like, what are the laws of thermodynamics?
Yeah, that's a good point. The second law of thermodynamics, in particular, often comes up when people are talking about TFH. That law says that entropy, which is a measure of disorder, always increases in a closed system.
Right, entropy. It's like the universe's tendency to go from neat and tidy to, well, my desk is a perfect example.
A perfect example, huh? So traditionally, we've thought of that second law as this absolute rule, but TFH suggests that it might not be so absolute after all.
Wait, are you saying that TFH might actually rewrite the rules of entropy? How is that even possible?
Well, remember, TFH is all about energy trying to reach equilibrium. So in a small contained system, like your desk, entropy might very well increase as things get more jumbled up.
Okay, I can see that.
Hmm.
My desk is definitely on its way to maximum entropy. But on a universal scale, things are a bit different, right?
Exactly. On a cosmic scale, it gets more complicated. While energy is spreading out, getting more evenly distributed, which seems like increasing entropy, at the same time, this energy is also forming incredibly complex structures. Things like stars, galaxies, even life.
So it's like order and complexity are emerging from this overall drive towards energy equilibrium. The universe is always creating these intricate patterns within this flow of energy.
Precisely. And that suggests that maybe entropy, the way we currently understand it, isn't the whole story. Maybe it's not always increasing. Maybe it fluctuates depending on how you're looking at it.
Man, this is making me rethink everything I thought I knew about the universe. It feels like TFH is more than just a theory. It's like a totally different way to see reality. But if it's so different, how does it even get accepted by scientists? What are the hurdles it has to jump over?
Well, one of the biggest hurdles, like with any new scientific theory, is experimental validation. It's great to have a beautiful theory that explains things in a really elegant way, but you gotta have solid experimental evidence to back it up.
So what kind of experiments could put TFH to the test?
Well, we talked about some possibilities earlier, like searching for those resonance zones in particle accelerators, or looking for specific distortions in gravitational waves. But there are other, more ambitious experiments we could do if we had the tech.
Ooh, give me some sci-fi scenarios here. What kind of experiments would really blow this thing wide open?
Imagine being able to create a tiny black hole in a lab.
Whoa, a mini black hole. That sounds kind of scary.
It would be a controlled experiment, of course, but it would let us study those extreme gravitational effects predicted by TFH up close. We could see how it affects the scalar field, how it changes the flow of energy and time around it.
Right, that one goes in the dream experiments file. What else? Any other sci-fi tests for TFH?
Another idea would be to build sensors that could directly detect the scalar field itself. Right now, it's invisible to us. But if we could build sensors sensitive enough to pick up those vibrations, we could actually see the universe as this swirling ocean of energy.
We could actually see those energy vortices that TFH says are particles? That would be incredible.
It would be a total game changer, but that kind of tech is still a long way off.
So we're not just waiting for better tech, though, right? Scientists can start testing TFH ideas now with what they have.
Exactly. And the more evidence we gather, the more we'll learn about whether TFH is a viable theory or just a really cool idea.
Okay, I am definitely seeing the potential of PFH. But even if it turns out to be wrong, it seems like it's already making us think differently about the universe. Asking these big questions, that's what science is all about, isn't it?
Absolutely. Sometimes asking the right questions is just as important as finding the answers.
This whole conversation has been so eye-opening. It's like I need to go back and reread all my old physics textbooks. TFH is challenging so many assumptions about how the universe works. But before we wrap up this part of our deep dive, you mentioned that TFH could have some pretty big implications for technology, too. Could you tell us a bit more about that? What kind of tech breakthroughs could this theory lead to?
That's a great question. And while we're definitely in the realm of speculation here, the possibilities are truly mind-blowing. If TFH is correct, and we're surrounded by this vast, untapped ocean of scalar field energy, then learning how to control that field could unlock technologies that would make even the wildest sci-fi seem tame.
Okay, now you've got my attention. Give me some examples.
Well, first off, imagine harnessing the energy of the scalar field directly. Forget fossil fuels, forget nuclear power. We could potentially tap into a clean, limitless source of energy.
Limitless energy. That would solve so many problems. We could power everything without harming the planet.
Exactly. It would be a total energy revolution, and it doesn't stop there. TFH also hints at the possibility of actually controlling gravity. Imagine vehicles that could levitate, maybe even fly, just by manipulating their own gravitational fields.
Flying cars. Now you're speaking my language. But is that really possible?
It's definitely super speculative, but if TFH is right, and gravity is just a result of how energy flows in the scalar field, then maybe, just maybe, we could find ways to create those energy gradients artificially.
Wow, that would change everything about how we travel, how we build cities, even how we live.
It really would. And who knows, maybe we could even manipulate space-time itself, creating shortcuts like wormholes, things we thought were only in science fiction.
Hold on, wormholes. Are you saying we could actually travel to other stars through these, like, tunnels in space-time?
It's super speculative. We're talking about pushing the very limits of physics as we know it. But the point is, TFH opens up this whole new world of possibilities that we're just beginning to explore.
I'm starting to see why you're so excited about this theory. It's not just rewriting the textbooks. It's about imagining a future that feels almost magical.
Exactly. Even if we never actually reach those sci-fi scenarios, the journey of exploring them could lead to some incredible discoveries.
Well, I'm completely hooked. This whole conversation has been mind-blowing. Before we finish this part of our deep dive into TFH, there's one more thing I'd like to talk about, something we've touched on a bit already. The philosophical implications. If everything is just energy flowing through this scalar field, what does that even mean for our understanding of reality? Are we all just temporary patterns in this giant cosmic dance of energy? So, we've been on quite a ride with this time force hypothesis, haven't we? Exploring how it reimagines, like, the very essence of the universe, the forces that shape it. But now I want to dive into the what-if zone. What if TFH is right? What could it mean for science, technology, even for humanity itself?
Those are the big questions for sure. And what's so exciting is that TFH doesn't just give us these new answers, it opens up all these new questions too. It's like it pushes the boundaries of what we even thought was possible.
One thing that really stuck with me was that idea of harnessing scalar field energy, Imagine a world running on a clean, limitless energy source. It almost sounds too good to be true.
It's a pretty mind-blowing possibility. And while the tech to directly tap into the scalar field is way beyond us right now, TFH gives us this theoretical framework that could guide future research.
So instead of relying on things like fossil fuels or even nuclear power, we could be pulling energy straight from the universe itself. That would be huge, not just for our energy needs, but for the planet too.
Oh, absolutely. And think about what it could mean for space travel. With a limitless energy source, we could power spacecraft that could travel incredible distances, maybe even reach other star systems.
Now you're talking. That's getting into some serious science fiction territory.
Ah.
But even if interstellar travel is still a long way off, TFH suggests we might be able to revolutionize space travel a lot sooner, by working with gravity itself.
Right.
Imagine spacecraft that have artificial gravity generators built in. No more worries about astronauts losing bone density or muscle mass in zero-G. We can build these big, comfortable habitats in orbit or even on other planets.
It's an amazing idea. And if we could really control gravity, the applications wouldn't stop at space travel either. Think about cities with buildings that float, transportation systems that shoot you across continents in minutes, maybe even personal hovercrafts. No more traffic jams.
Okay, now I'm picturing flying cars zipping between skyscrapers. That's both exciting and a little scary to think about. But before we get too carried away with these futuristic dreams, let's come back down to Earth for a minute. What about the more immediate effects of TFH on scientific research? How could it change things now?
TFH has the potential to change so many fields of science, not just physics. For cosmologists, it gives them new ways to study the Big Bang and how the universe has evolved. It might even give us clues about what was happening before the Big Bang, something that's always been a mystery.
So instead of running into a dead end with the Big Bang, we could use TFH to look further back in time, to the universe's earliest moments.
It's definitely possible, and it's got cosmologists pretty fired up. And then there's the whole mystery of dark matter and dark energy.
Yeah.
TFH actually offers explanations for both, suggesting they're not some exotic new particles or forces, but actually just emergent properties of the scalar field itself.
So we might finally crack the code on those cosmic riddles that have baffled scientists for, forever.
It would be a huge breakthrough. And it doesn't stop there. TFH could revolutionize how we understand particle physics, too. It could lead to new discoveries and technologies based on manipulating the scalar field at the quantum level, really small scales.
It sounds like TFH is less of a theory and more of a paradigm shift, a whole new way to look at the universe and everything in it.
I think that's a great way to put it. It's a shift that could have these really profound implications, not just for science and tech, but for how we understand ourselves and our place in the cosmos.
And that brings us back to those big philosophical questions.
Yeah.
If everything really is just energy flowing through the scalar field, what does that tell us about consciousness? About what it means to be human, about the meaning of existence itself? Those are some heavy questions.
Those are questions that philosophers have been wrestling with for centuries, and TFH doesn't necessarily give us clear-cut answers. But it does give us a new perspective. It invites us to see ourselves not as these separate, isolated beings, but as parts of this incredible interconnected web of energy that makes up the whole universe.
So maybe instead of feeling small and insignificant in this vast cosmos, TFH can help us feel more connected to everything around us, like we're part of something much bigger.
That's a really beautiful way to think about it, and maybe that feeling of connection, of being part of this grand cosmic dance, is one of the most amazing gifts that TFH offers.
Well, I think we've reached the end of our deep dive into the time force hypothesis. We've covered a ton of ground, from the basic concepts to the potential impact on science, technology, and even our philosophical understanding of the universe.
It's been an incredible journey, that's for sure. And even though TFH is still pretty new and hasn't been fully tested, it's definitely sparking conversations and pushing us to think beyond what we thought was possible.
I'm left with this sense of wonder and awe, and also a newfound appreciation for human curiosity. That drive we have to understand the universe and our place in it. So to everyone listening, we leave you with this thought. If the universe really is this amazingly intricate tapestry woven from the threads of a single fundamental energy field, what other secrets might it be hiding? What other incredible discoveries are out there waiting for us as we keep exploring?
And maybe even more importantly, how will those discoveries change how we see ourselves, our purpose, our role in this incredible cosmic adventure?
Thanks for joining us on this deep dive into the time force hypothesis. Until next time, keep exploring.